Okay, so we're going to go over chapter 8 in this video. There are 7 key concepts that I want you guys to take away from this. You will notice that I am not starting on the first slide of the PowerPoint that I posted in the folder out on Moodle. I'm starting on slide 7. Go ahead and read the ones before it, just give you some examples on calculating mass and average mass using marbles and things like that. But what I want to do is start here on slide 7 with determining atomic mass. So your first key term that you need to understand is atomic mass unit. And this is not your first exposure to AMU. We talked about this when we were talking about isotopes. So the average atomic mass is a weighted average of the masses of all the isotopes of an element. Okay, so if I go out here and show you, we know where to find that, right? On the periodic table, let's look at carbon. 12.01 is the weighted atomic mass, the weighted average mass, the AMU for carbon, the weighted mass of all the isotopes. Okay, so we're going to start using those numbers there and putting them into some calculations. I'm going to go back to the PowerPoint. Okay. So 1 atomic mass unit, 1 AMU equals 1.66, I can talk, sorry, I'm not re-recording this again. 1 AMU equals 1.66 times 10 to the negative 24 grams. Okay, so we're going to keep that in mind. So even though carbon does not contain a single atom worth that mass that's listed on the periodic table, it's treated as though it's composed of only one type. And that's the number that we're going to be using that's listed on the periodic table. Okay, so they're posing a question here. How would we calculate the mass in AMU of 431 atoms of carbon? So the mass of one carbon atom is 12.01 AMU. That's what we got from the periodic table. We want to use this relationship as a conversion factor. So this looks like the dimensional analysis that we were doing. Let's kind of take a look. We've got 431 carbon atoms. We want to convert it to AMU. We know that the mass of one carbon atom has 12.01 AMU per one carbon atom. We're setting it up to get rid of the atoms, so they're going to cross off diagonally, and we're going to be left with AMU as a unit. So we've got 431 times the 12.01 will give us 5,176 AMU. Okay. Let's look at calculating the mass in AMU of a sample of aluminum. They're saying that we've got a sample that contains 75 atoms, so we have 75 aluminum atoms. So this 26.98 AMU for one aluminum atom, that's from the periodic table. Let's go take a look again. Okay, so let's look at aluminum. So aluminum is right here. Let me see if I can zoom in a little bit. Okay, see on aluminum here, 26.98. That's the number that we're using. And I go back to the periodic table. So it's 26.98 AMUs in one aluminum atom. So the atoms will cross off, and you're only going to be left with AMU. And when you multiply across, you end up with 2,024 AMU. That is the mass of a sample of aluminum. Okay, so this is another key concept you guys have to, you're going to hear it a lot, and it's called a mole. And it's not the little animal, it's spelled the same, but it's not. So the definition of a mole is the number equal to the number of carbon atoms in 12.01 grams of carbon. So a mole of anything, look at this number here, a mole of anything is 6.022 times 10 to the 23rd units of that item that you're talking about. That is called Avogadro's number, and that's another key concept. We've got 3 so far. We've got AMU, mole, and Avogadro's number. So 1 mole of carbon is equal to 6.022 times 10 to the 23rd carbon atoms, which is also equal to 12.01 grams of carbon. These are equivalents. Okay? So let's take a look at a couple of these. So if you have a sample of an element with a mass equal to the element's AMU, expressed in gram, it contains 1 mole of atoms, which is the Avogadro's number. Okay, so let's just take a look at the numbers here. So if we have aluminum, We just looked at this one. The number of atoms present is 6.022 times 10 to the 23rd. The mass of the sample in grams is 26.98. That's the number we got from the periodic table. They're kind of interchangeable. Look here, all of these numbers of atoms present are all the same. It's all Avogadro's number. So what we're going to be focusing on are the elements that we're looking for and the mass of the sample, which is the number that is below the element symbol on the periodic table. So if we take a look, let's just double check. Why don't we look at iron? Okay, 55.85. So if I go over here to the periodic table and look at iron, okay, so where's iron? Right here, 55.85. This is 55.85 AMU. It's also 55.85 grams. Keep that in mind. We're baby stepping this here, okay? I'm going back to the PowerPoint. So any of these elements that you look up, these are the numbers that you should see under their symbol on the periodic table. Oh, I'm going to go back one, and now I'm going to go back over to the webcam. We're going to do some examples of this and try to figure out what exactly we're doing. Okay, so let me go over to the webcam. There's my big old arm in the middle of it. I'm going to pause it for just a second while I get my pen and paper ready. Okay, I'm back. There was a piece of paper that had writing on it, and I wanted to get a blank one. And we are going to do a couple equations for this. So if we wanted to determine the number of copper atoms in a 63.55 gram sample of copper, okay, let's try to figure out the number of copper atoms, and then we're going to figure out the closest average mass of one atom of copper, okay? So let's kind of put it all together in one big equation and then we'll pick it apart. So I'm going to start with one copper atom. Oh, I'd be marked down for that one. This should be a capital CU. Well, you guys know that that's right. CU, copper. Sorry. One copper atom. We're going to multiply that by the 6.022 times 10 to the 23rd. Remember Avogadro's number? So the atoms have to go on the bottom. So we've got 6.022 times 10 to the 23rd copper atoms in 1 mole of copper, okay? Now, we want to end up with grams. So this is where we're going to look at the number on the periodic table, where we're looking at grams. The number that's listed on the periodic table for copper is 63.55 grams. That is the amount of grams that are in 1 mole of copper, okay? So if we multiply this across, let's get rid of our diagonal units. So atoms are going to go away, moles are going to go away. We are left with grams. And when we multiply that across, I'm going to write it down here because I ran out of room again. We're going to end up with 1.055 times 10 to the negative 22 grams of copper, okay? That is the closest average mass of one atom of copper. This is the closest average mass of one atom of copper. Okay. Sorry, got to keep it on the page here. Okay, let's just look at one more, and then we're going to go on and we're going to work on calculating what's called molar mass, which is what's going to help you guys with your stoichiometry lab, figuring out how to get molar mass, and then we will actually be doing a separate video on the stuff from chapter 9. Okay, so let's calculate, divide that out. Let's calculate the number of iron atoms in a 4.48 mole sample of iron. Okay, this is a little bit different. It's worded a little bit different, right? Okay, let's start with what we know. Okay, so they've given us 4.48 moles of iron, right? We would like to get to atoms of iron. That's what they're looking for over here. So if we multiply, we want to put moles on the bottom so that we can get rid of moles kitty corner up here. So we're going to put 1 mole of iron. What did we learn about with Avogadro's number? It always has the same ratio, right? So 1 mole is 6.022 times 10 to the 23rd atoms of iron. Sorry, hope it's entertaining for you guys, okay? So moles of iron are going to cross off. We're left with atoms of iron, right? So if we multiply this across, again, I'm going to write it down here because I'm writing large today. You're going to end up with 2.70 times 10 to the 24 iron atoms. Okay. These are good conceptually to know. We're going to be taking it a step further, and we're going to be calculating molar mass when we add more than one element together. So we're going to be looking at the overall mass in a compound. Let me go back over to the PowerPoint. Sorry, giant arm again. All right. Okay, so let's look on the PowerPoint here. And, okay, so we are going to be looking at solving problems conceptually, I guess is a good way to put it. All right. What that means is we're going to be reading problems and trying to figure out what we know, where we want to be, and how we get there. I guess is a good way to summarize it up. Okay. So we're going to be, here's another one of your key concepts. This is molar mass, and you will hear this a lot. You will be using this from here on out in this class. Okay. So the mass in grams of 1 mole of the substance. So you guys saw me before I wrote down the grams per mole. This is what that is telling you. We're telling you how to get it. So molar mass of nitrogen is 14.01 grams per 1 mole. So I'm going back over to our periodic table. Let's go look at nitrogen. Okay, nitrogen is up here. Let's look at the number, 14.01 grams in 1 mole of nitrogen. Okay. Okay. Molar mass of chlorine. If we look at chlorine, the 35.45 grams per mole, chlorine should have 35.45 on the periodic table. Let's take a look. Where's chlorine? Right here, 35.45. Okay, so you guys see the pattern that's happening here, right? Okay, so I'm not sure what just happened, but it looks like I need to pause this. I don't know if we just lost our stuff that I was talking about. Ruh-roh. Hold on. Okay, I'm gonna hope that there isn't a big gap here. And if there is, that means I have to record this again. So cross your fingers. So whatever just happened with my Zoom button, it looks like it's back. So we were just talking about molar mass with grams per mole. So let's look over here. So when we're doing calculations for molar mass, we're looking at moles of a compound. So the moles of the compound is equal to mass of a sample over the molar mass. So moles equals grams, and the molar mass is grams per mole. Okay, so if we're looking at, let's do a couple examples to see if this might help you a little bit. Okay. So what we're looking at calculating, we want to calculate molar mass of a compound. So if we are calculating molar mass, let's look at water, right? We know water, H2O. We want to look at what is involved in the compound and how many of them there are. So let's break it down a little. We have hydrogen, and there are 2 hydrogens. We have oxygen, and there is 1. We don't really have to multiply it by 1 because it is going to be what it is, but let's just put that out there. So if we were to look at the periodic table for hydrogen, let's look at the grams per mole. We're going to be looking at grams per mole for calculating the molar mass. I hope you're enjoying this. I don't know what's going on, but things just keep resetting here, but hopefully we're going to be okay here. So if we go look, or I'm just going to tell you, if you look at hydrogen on the periodic table, it is 1.008 grams per mole. That is what is listed under the element symbol on hydrogen for the grams per mole. Okay. On the oxygen, we should be seeing 16.00 grams per mole. Okay. Oxygen is fine as it is. Hydrogen, we have 2 hydrogens, which means we need to take this number and multiply it by 2. Okay, so I'm going to do this. I'm going to say times 2. Right? So when we multiply that times 2, I'm going to actually kind of round up a little and do 1.01 just for numerical ease. Okay, we'll do that. So if we multiply that, we're going to end up with 2.02 grams per mole. And it's okay if you're rounding a little bit on your periodic table as long as you're getting pretty close for now, just while we're getting the concept down. So if I take the 2.02 and add it to the 16.01, let me just carry this over here. So 16 added to 2.02 is going to be 18.02 grams per mole. 18.02 grams per mole is the molar mass of water. Okay, so it's a calculation. We're going to be looking what's in the compound, and we're going to be pulling the grams per mole, the molar mass, off of the periodic table, and we're going to be adding all of the molar masses together to get 1 molar mass for that compound. Okay, so let's do one more. Let's see what the molar mass of barium nitrate is. Okay, this is going to be a little bit more complicated, but just split the stuff out. See what we have here. So we've got barium. And if we look at barium on the periodic table, it's 137.33 grams per mole. Okay. For the nitrate, I know I've told you guys keep your polyatomics together. You actually need to separate them out right now unless you want to find out. You could find out the mass of nitrate and multiply it by 2. I'm going to take both items within the brackets and we're going to get separate molar masses and add them together. So let's just look at nitrogen. Nitrogen has, there's 2 of them in there. Remember, on the outside of the bracket applies to everything inside. So we're going to find out nitrogen has 14.01 grams per mole times 2. So that's going to be what? 28.02 grams per mole. Okay. Look at oxygen. How many oxygens are there here? You've got 3 in the bracket times 2. You're going to have 6 of them. And oxygen has 16.00 grams per mole times 6, okay? And if I had a calculator, I would do that right now, but I know the final answer, so we'll figure it out. Sorry, I'm going to pause you for a minute. I'm going to actually get you a calculator on here that we can use. And nope, sorry, did not find a calculator, but if we multiply 16 times 6, we're going to get 96. Okay, so then we're going to add them all together. Let's just carry this guy over here so they're all nice and even and lined up. So we have the grams per mole for barium, the grams of the 2 nitrogens, and the grams per mole of the 6 oxygens. If we add these together, we should get 261.35 grams per mole. This is the molar mass of the barium nitrate. Okay. All right. So I can try to post some examples if you want, some sample problems, but this is just one of those that, just the pattern. You're going to be pulling the numbers off the periodic table and combining them together for all the different parts that are in that compound. So let's go take a look back at the PowerPoint. Okay, so this should make a little more sense now when you look at it. Okay, so here's another one of the terms that we're leading up to one of the terms, one of the other ones you need to learn here. There's something called a mass percent of how much of an element is in a compound. Okay, so what you're going to be doing is you're going to be taking the mass of the element that's present in 1 mole divided by the mass of a mole of a compound to get the fraction. And that sounds a little confusing, but we're going to walk through it and see what we can do here. So let's look at this, ethanol, C2H5OH. It contains 2 carbon atoms, we can see that there from the subscript, 6 hydrogen atoms. Well, we have 5 here plus 1 more here. This is just how the molecular formula is written out. And then we have 1 oxygen. This means that for each mole of the ethanol contains 2 moles of carbon atoms, 6 moles of hydrogen, and 1 mole of oxygen. So we calculate the mass of the element that's present and the molar mass for the ethanol as follows. So I put this in here so you guys can look back at it. So let's take a look. The mass of carbon, we have 2 moles, there's 2 of them, times the molar mass from the periodic table. This is just what we were doing, the 24.02 grams, okay? The mass of hydrogen, we have 6, so we have the 1.008, or you can round it to 1.01, is going to equal 6.048 grams for hydrogen. The mass of oxygen, there's only 1, is the 16 grams per mole. We end up with 16. So the mass of 1 mole of ethanol is going to equal 46.07 grams, which is the molar mass. That's adding all these up together. Okay. To find the mass percent, now this is another one of your key terms, it's also called the weight percent, of just one of the elements in there. So let's just look at the carbon in the ethanol. We want to figure out what is the percent, the mass percent of carbon in this overall molecule. Okay, so we're going to compare the mass in 1 mole of, the mass of carbon in 1 mole of ethanol with the total mass of 1 mole of ethanol, and you're going to multiply it by 100% to get your percentage. So let's look at how it's set up here. We have mass percent of carbon. So we have the mass of carbon in 1 mole and the mass of 1 mole total, okay, times 100. What numbers, where are we pulling these? Well, the mass of 1 mole is what we found out here. That's the molar mass. See how down here they have the 46.01? Go back 1 slide. Look at the mass of carbon. 24.02 grams is what goes on top. If you look down here, so we're looking at what percentage of carbon is in the overall percent of the compound. We end up with 52.14%. Oh, I'll come back to this one. Okay, so we're going to go over to the webcam again. We're going to do another one, okay? All right, so let's look at mass percent. I want to calculate, we're going to do a couple things here. I want to calculate the molar mass of morphine. That's an O, morphine. Okay, my spelling, you guys know me. I want to get the molar mass, and I'm going to divide it, the mass of the element that I'm asked to look for to try to find out the percent, the mass percent. So let's write out this question. So if we have morphine, spelled correctly there, morphine has the formula C17H19NO3. Okay, we want to find the percent mass of carbon in this compound. Okay, so our first step here, where I wrote it up here, is calculate the molar mass of morphine. So we're going to put this down here. Let's find the molar mass. Break down what you have here. Let's write them in a column. So we have carbon, and carbon is 12.01 grams per mole. How many do we have? We have 17. Times 17 is going to equal 204.17 grams per mole. Okay, let's look at our next one. We have hydrogen. Hydrogen, I'm going to do the 1.01 grams per mole just for mathematical ease, times 19. We have 19 of them, right? Which is going to equal 19. Hi, 19.19 grams per mole. Sorry, my screen keeps going blank on me here, you guys. I hope it's not doing that on your end. Okay, so the next one we need is nitrogen. We only have one nitrogen. Nitrogen is 14.01 grams per mole times 1 is 14.01. I like to do this so I have them all lined up and I can add them up a little bit easier that way. You can do it however works best for you. There is something showing through on the bottom here, so I'm going to move that guy. All right. Okay, what do we have left here to find? Oxygen. So we have oxygen is 16.00 grams per mole times, we have 3 of them. That's going to equal 48.00 grams per mole. We want to add them together. So the molar mass is going to equal 285.37 grams per mole. So that's the molar mass of morphine. Okay, so now we have to go back to the question. We want to look at the percent mass of carbon in this compound. Okay, so if we take the molar mass of carbon, which is 204.17 grams per mole, right, divided by 285.37 grams per mole, which is the total molar mass for morphine, right? This is going to equal 0.176, and then we want to multiply it by 100 to get a percentage. So what are we going to end up with? Oh, did I do the wrong numbers? Hi. Hold on just a sec. And I'm back. I didn't really do the wrong number. I just read it wrong off of my paper. So when you multiply, you're going to end up with 0.716. I flipped 2 of the numbers, so that makes more sense to me. So times 100, you're going to end up with 71.6% carbon. Okay, so that is how you find percent composition of a compound. So I'm going to pause you one more time here. Okay, we are back on the PowerPoint. Okay, so we have two more key terms that we need to know from this chapter. One of them is called empirical formula, and the other one is going to be molecular formula. So we're going to look through the slides just a little bit here, and then I'm going to, sorry, I'm reaching for paper. Then I'm going to actually give you an example that I think makes a little more sense than the slides, but let's just sort of walk through it a little bit on here. So empirical formula is the formula of a compound that expresses the smallest whole number ratio of the atoms present. And it can be found from the percent composition of the compound, what we just learned how to do. So let's look at this. An empirical formula, we see here carbon, hydrogen, simplest whole number ratio, okay? The molecular formula, which is the empirical formula times some number, is going to give us the answer to the molecular formula. So this is the actual formula compound. The empirical formula is how it's expressed as the smallest number whole number ratio. I know the words are a little bit funny. So like I said, bear with me for a minute. We're going to walk through this just a little, and then I'm going to give you some examples, okay? Let's see how confusing this gets. Why don't I go over and I'm going to do an example right now, and you can go back after I do my example and look through the rest of the slides and see if that example makes sense to you. But let's do one on paper together. Okay, I'm back. There's my arm. Okay, so to find an empirical formula, we're going to assume a couple of things. Let's say we have 100 grams. Oh, let's do sig figs. Let's say we have 100.0 grams of a compound. Okay, that's going to be handy if we have 100 because we're going to be able to get round numbers from percentages. So if we have 100 grams of a compound, and let's say we have 80 grams of carbon and 20 grams of hydrogen. Okay. First of all, let's figure out how many moles of each element we have. So number of moles of each element. Okay. Let's start with carbon. So if we have 80.0 grams of carbon, we want to get rid of grams and we end up with moles. So looking at the periodic table for carbon, we know that it has 12.01 grams of carbon per 1 mole of carbon. So if we multiply across, we're going to end up with 6.66 moles of carbon. Okay, that's good. That's one of the numbers we need. The other one we have to work on is hydrogen. So if we have 20.0 grams of hydrogen times, we want to get to moles, so we're going to times it by 1 mole of hydrogen, and the molar mass from the periodic table is 1.01 grams of hydrogen per 1 mole. This is going to give us 19.8 moles of hydrogen. Okay? You can hear me turning papers, I'm sure. So then what we want to do is we want to figure out the ratio these elements have to each other. Or I guess to put it in, look at the number of moles you found and divide them both by the smaller ones. So if you have 6.66 moles of carbon, right? Divided by 6.66 moles of carbon, you're going to equal 1. if we take our 19.8 moles of hydrogen and you divide it by 6.66 moles of carbon, you're going to get 2.97. Okay. So then what you're going to do is you're going to write the empirical formula based on what we just got. So the calculations above shows that the ratio for carbon is 1. So the ratio for carbon is 1, and right there, the ratio of carbon to hydrogen is 3. So is 3. So I'm going to put the ratio is 3. So what that means is when we write it out as an empirical formula, we have carbon has a 1 subscript, invisible, and hydrogen has a 3. So the empirical formula for what we have just done is CH3. Okay. We will be needing to now figure out the molecular formula from the empirical formula. So this is the empirical formula. Okay. Put it all on the screen. So to find the molecular formula, what we're going to do is figure out the molar mass of the actual molar mass of the compound. So CH3 would be, hang on, my screen's going out funky again. Just a minute, you guys, hang on. Okay, I can't wait to review this video, you guys, to see what's happening. I hope it isn't all fluggy all over the place because I'm gonna have to do this all over again. So cross your fingers. So we figured out the empirical formula is CH3, right? Okay, so let's find the molar mass of the empirical formula. So the molar mass is 1 carbon, 12.01 grams per mole, right? And the hydrogen is 1.01 grams per mole times 3. So we have 3.03 grams per mole. Okay, so this is 15.04 for the CH3. Okay, we're going to divide the molar mass that's given to us in the problem by the molar mass that we actually found. So the molar mass that we found in the problem from the other page that we were working on was, where's our molar mass? Just a minute. Okay, the reason I didn't know what they were talking about on here, and I'm copying over some notes, is it was off of another problem. So we're gonna assume that the molar mass in the original problem, so the actual molar mass is 30.14 grams per mole. Okay. So all you're going to be doing to get the molecular formula is you're going to take the molar mass from the empirical formula and put it down here. So we're going to take 15.04 grams per mole divided by the actual molar mass that's given in the problem. You didn't know that. I'm just giving it to you now. So we'll just go with it and just see the process. So it's divided by 30.14 grams per mole. Okay. When you divide that out, you're going to get 1.977, which is the ratio. So what that means is you're going to end up, we're going to round this up to 2. This number is going to get multiplied. I'm going to say you multiply it by the empirical formula. So the subscripts, by the subscripts. in the empirical formula. So we have CH3, right? We're taking this number 2. So C has an invisible 1. So C times with the invisible 1 times 2 is going to be C3. No, it's not. It's going to be C2. C2, I added. Don't add. Do what I do. So it's C2. And then you've got your H3 times 2 is going to be H6. So this is what your molecular formula should be. I will try to find some other examples to put out there for you. This is a concept that can be pretty confusing, especially when we aren't in class for you to ask questions, but let's just kind of go with that, okay? I'm going to pause this and go back to the PowerPoint. Okay, so what you guys can do based on what I just showed you with the empirical formula and the molecular formula, there is a problem here in the PowerPoint that goes from slides 21 through 26. Go ahead and work that out and see if you can get to the answer that we've got here in the PowerPoint, okay, based on what I was showing you how to do. I know it's kind of a confusing concept. I will review this again, but I wanted to get these concepts out to you so that when I start talking about the stuff in chapter 9, they'll make more sense, because you need to be able to calculate molar mass in order to do the equations that we're going to be doing with stoichiometry. And I know you guys have the lab that's due by Sunday on stoichiometry, which is why I'm kind of pushing through these 2 chapters so that you have a foundation to complete the lab. Okay, so I will move on to the next video.